Hello everybody. In this video we are talking about partial derivatives, which is from 14.3, and let's first look at the definition. Maybe before definition it's better to recall the definition of the derivatives in the single variable calculus, which is calc 1. So if you're given a function f of x, then what is f prime x? Sometimes we can write this as df of x dx, which means when you differential of f of x, you can think of difference of f value over difference of x value and take the limit. So that is given by difference of f value and difference of x value. When I look at the difference of x value, x plus h minus x, the difference is h, so h. But h should be getting smaller and smaller, going to 0. All right, now we look at the definition of partial derivatives. So you're given f of x, xy. There are two variables, and we're looking at partial derivative with respect to x, not y. Then this is essentially the usual derivative in single variable calculus, but y is just a fixed constant. So y is treated as fixed constant, just like 1 or 2, and x, you're only taking derivative of x. So formally we write this definition as partial f partial x, and with the target point, and the definition is in the limit language. So change in f value and change in x value, not y value, and h should be going to 0. Now, so from this definition, y0 did not change at all. So it's just like constant, it's frozen there. So the partial derivative notation can be written as usual derivative notation, but we specify the running variable is x. And y0 is just frozen. Y value is frozen at y0. And after we compute the derivative with respect to x, then we can put the target value for x. And there are a few other notations like this, this, this. Those are all the same. We will use that time to time. Now, again, f of xy, now we can talk about partial derivative with respect to y. In other words, x is frozen and y is changing. So what it means is the notation is df dy and target point. So y is changing, x is frozen. Or you can write this as d dy and x0 is frozen and y is changing. So take the derivative and put the y's target value, and which is limit of change in f, but here x0 is frozen and y0 plus h and y0, they're changing. So this is change in y. Now we can look at this question, example 1 for computation. We are going to go through a series of examples, 5 or 6 problems, and try to get familiar with this procedure, partial derivative. All right, so for the first one, df dx, what we're going to do is we take derivative term by term. What is x squared? Because x squared, x is changing variable, it's not frozen at all. So just x squared prime is equals 2x. So I just put 2x. When I look at here, this is a tricky one. So when I look at 3xy, Then 3xy prime, I'm looking at y as constant, just like 3. So I put this as 3y as a coefficient, and x is the variable only. So this is 3y. You can put this. And x prime is just 1. So this is 3y. And for the last two, y minus 1, y is constant, frozen. So constant prime is just 0. So at the end, we want to put the target point for negative 5, which means replace x by 4, y by 5, so negative 15 plus 8, negative 7. So this is the first question. The second question, what about partial derivative with respect to y? Then again, term by term. What is x squared prime? Here by prime, I mean y derivative. So in other words, x is frozen, just like 2. Then constant prime is 0. So 0. And 3xy. Next is 3xy. 3xy prime. Now here x is frozen, only y is changing variable. So this is 3x. You can take out this coefficient anytime from derivative, and y prime is just 1, so 3x. And lastly, we have y minus 1. I'm going to put that together. So y minus 1 prime, because I'm taking y derivative, so this is just 1. And put the target value for negative 5. Then this is 3 times 4 plus 1, which is 13. All right. Now next problem. We only need to find partial derivative of with respect to x and y as a function. There's no target point. So we just need to compute. For this problem, this is partial derivative for the computation. And then at the end, because of target point, you want to put this target point into x and y in the previous partial derivative. But there's no last step for substitution. We only need to find fx and fy for its formula as a function. So f is given by 2y y plus cosine x. So we assume you still remember chain rule and every basic rules of the different single variable calculus differentiations. So we look at d of dx. So y is frozen. For this case, 2y is constant. This is y is also constant. You can think of y as 1. Then this is 2 over 1 plus cosine x. So you can think y equals, let's say, 1. Then how do you compute 2 plus 1 plus cosine x prime? This is similar question, simplified question. Then by chain rule, this is 2 times 1 plus cosine x square, negative 1, times 1 plus cosine x prime. This is chain rule. So this is how you compute them. Now for this problem, when I get back to y here, exactly the same thing happened. I will write this 2y first, and then this is 1 plus y plus, sorry, y plus cosine x square, negative 1, times the chain rule. So y plus cosine x prime, but in this term, this prime means d dx. or you can write partial x. Then we have y plus cosine x squared and negative 2y. When I look at here, because y is constant or frozen, so x derivative of y is 0. And cosine x prime is negative sine x. Negative sine x. So if we compute, simplify, there's nothing too much for simplification. So that's the end. And what about then partial f, partial y? In this case, we're going to use quotient rule. So if recall the quotient rule, it's that fg prime is f prime g minus fg prime. So we have f here, g here, and x is frozen. So what, by quotient rule, we can get, we need to square in the denominator and numerator 2y prime, but y prime, which is, I would write this way, partial y, and times y plus cosine x minus 2y times partial y of y plus cosine x. We copy the denominator and the numerator. So if we take 2y prime, then this is just 2, because y derivative, right? So this is 2, y plus cosine x minus 2y. When I look at this is partial y plus cosine x. Cosine x is a constant because this is frozen, so constant prime is 0. But y prime is 1, so this is 1. If we rearrange or simplify, the only thing we can do is numerator. So 2y minus 2y is 0. So 2 cosine x is the only term in the numerator. Okay. Now, exercise example 4. We want to find the partial derivative of z with respect to x, assuming that this equation. In this equation, usually a function is given by z equals z of xy. So, or you can write this as z is a formula of f of xy, something like this. However, this is called explicit form. Explicit. But in this case, we cannot directly write z in the explicit form, so this is called implicit form. So for implicit function, we often use chain rule to find its derivative. Because z and x and y's are mixed together. All right, what is partial derivative with respect to x? And to do that, what I do is I will take derivative, x derivative, both sides. So what it means is I will do partial x of yz minus log z, partial x plus y. One thing we want to memorize, not memorize, emphasize is partial z, partial x is something we want to find. Sometimes I can write this as zx, but partial x, then that is just 1, obviously. This something divided by itself is 1. But partial y, partial x, this is 0 because y is frozen. So for this problem, when I look at here, we can break this down into several terms. When we look at the first term, partial x, y, z, you're taking derivative with respect to x. So y is frozen, constant. You can take this out. And then the remaining thing is partial xz. Partial xz is something, so the question we want to compute out. So the first one is y partial xz minus. And for the second term, partial x log z, we have to use chain rule. It's, if we take log z derivative, then this is 1 over z, but we're not taking derivative with respect to z. We're not taking derivative with respect to x, so we also need zx. Or you can write this as partial xz. That's the same thing. So in this case, we have 1 over z partial xz. And partial xx is 1, and this constant prime is 0. Now we need this thing which can be factored out. Y minus 1 over z equals 1. And then we can solve for partial x at z, which is this. And we don't want to leave it as complex fraction, so multiply z on top and bottom, then this is z, and this is yz minus 1. All right, so yz minus 1. Okay, this is the answer for first partial x. Now, what about partial z, partial y? Then to do that, we want to take derivative partial y to both sides. So partial y and yz minus log z. I'm actually looking at this line, but I change x by y equals partial y x plus y. Now this time we freeze x term, but y term is not frozen. So when I break this down, the right hand side is straightforward. X is constant prime is 0. So partial y is 1. Now let's look at the first term. What is partial yz? If you choose to change y or run y, then this first term is changing. And z is as a function of x and y. If you change y, then z value is also changing. So both are changing. Then you cannot, both are not constant, in other words. So you have to use product rule. So the product rule is fg prime, then f prime g plus f g prime. That's the product rule we were going to use. So for here, this is partial y times z plus y times partial y z. And partial y is 1, so this is z plus this one is just copy. No, plus, so partial yz. So the first term becomes z plus y partial yz minus, this is chain rule, so 1 over z times partial yz equals 1. And then we can, from here, we can take out partial yz and 1 y minus 1 over z. And this z term can be moved to the other side, so 1 minus z. And partial yz equals 1 minus z, y minus 1 over z. And now multiply z on top and bottom. We come up with this fraction. Okay, now next we look at example 5. There's a geometric object in 3 dimensions, which is paraboloid given by z equals x squared plus y squared. And if you intersect this paraboloid by the plane x equals 1, so this is the plane x equals 1. So x equals 1 intersects the 3-dimensional paraboloid in a parabola as we see it in the blue line. Then find the slope of tangent to the parabola at 1 to 5. So this is 1 to 5 point, and if you draw a tangent line, then this is red line. I want to know what's the slope. This one is relatively easy as long as you understand what they ask for. So the slope of this tangent line, because x equals 1 is the whole plane, so x equals 1 is frozen. X is frozen at 1. So the slope is actually looking for the derivative with respect to y. So you are changing y. If you change a little bit y, then the function value will change, but very close to this straight line, which is called tangent line. So here what we're looking for is zy. And after you find zy, then you want to put 1 to 5 in there. So what is zy? X squared y squared is z. So this is partial y, x squared plus y squared, and 1 to 5. And from this partial derivative, y is running, but x is frozen. So constant prime is 0. And y squared, take derivative, that's 2y. And put 1 to 5. Here 1 to 5, 1 is x, 2 is y, 5 is z. So that's what it means. So this is for y, we only choose 2. So this is 4. The slope is 4. All right. We can also talk about multivariable calculus with functions of more than 2 variables. So something like 3 variables. And the definitions of partial derivatives of functions of more than 2 independent variables are similar to the definition of functions of 2 variables. So we had a few examples of 2 variable functions, but It's exactly the same. So when you have three variables like f, x, y, z, then what is partial derivative with respect to x? Then you can write this freezing y and z. So only change x and do not change y, z, and then divide by the change in x. Now, they are ordinary derivatives with respect to one variable taken while the other independent variables are held constant. That's what it means. Y, z's are frozen. All right. This is the end of this lecture, and we will have some homework problems in the three variable functions and partial derivatives.